In this tutorial, we're going to examine using S parameters to find some useful information about transistors that we're going to design for power amplifiers. If you're following along in my ECE 5321 class, you can select the Cascode transistor _SP simulation and open the schematic. In this simulation, we have a cascode stack of transistors, and we have a voltage source, sinusoidal voltage source that we're placing at the gate of a transistor, and a second voltage source, a DC voltage source, that we're using to bias the gate of the cascode transistor as well as the drain of the cascode transistor. We're biasing the transistor through a large inductor, 100 nanohenries. This inductor just needs to be a large impedance at the design frequency. We're isolating the AC signal from the DC signal using a big DC blocking capacitor, which has to be a low impedance at the design frequency. Finally, we've added a port that we're going to use to measure the S parameters looking into the drain of the transistor. Note that we can place a port anywhere and look at any pertinent information that the S parameters can yield us, and we can even do a two-port simulation. But right now we're only looking to find what the drain capacitance is of this device. Let's examine the voltage source. We've placed a DC voltage source on the signal that's equal to half the difference between the peak voltage allowed, 1.8 volts, and the threshold voltage of 0.4 volts. We've also set an amplitude of 700 millivolts for the sinusoidal signal and set a frequency of 5 gigahertz. This isn't important for a standard S parameter simulation, but for a large signal S parameter simulation or a PSP simulation, we need to have this information. S parameter simulations are small signal and are agnostic to amplitude of this, to any amplitude or DC settings of the signal. With this, let's open up our simulation by going to Launch ADEL and opening up the save state that, again, you have access to if you're part of my 5321 class. If you're not, you need to set up the model libraries appropriately. Now, we're going to set up an S parameter simulation and run that first, and then we'll examine the large signal S parameter simulation. We open up the analysis tool, click on SP, and select our port. In this case, we only have one port to select since we're doing a one-port S parameter simulation. We're going to sweep a variable, frequency, and we're going to sweep it from 4.5 gigahertz to 5.5 gigahertz, and we can just leave the automatic sweep set. Now let's run the simulation. Note that in this case I've written an equation that automatically estimates the capacitance. It does so by using a design equation The design equation looks like so. We take the imaginary part of the Y parameters looking into the port, wrong equation. We take the imaginary part of the Y parameters looking into the port and divide by 2 pi times the frequency, and we extract the frequency by selecting the X value of the imaginary part of the Y parameters of the S parameter simulation. We write this equation and select it to be plotted. The capacitance versus frequency is plotted after we run the simulation. We can, of course, access the S parameters or Y parameters by going to Results, Direct Plot, Main Form. We can select S parameters and plot S11 in many different ways. This is essentially the reflection coefficient, and we can convert the reflection coefficient into an impedance or an admittance using appropriate formula, or we can let the simulator do it for us by selecting the y parameters, and we are interested in the capacitance looking into the drain, so we would select the imaginary part of the y parameters and plot those. Since we are just looking at essentially at a capacitor, we should see that the y parameters increase linearly with frequency. In other words, this is the same as the shunt susceptance, which linearly increases as frequency increases. When we're designing a power amplifier, we have to be concerned with large signal perturbations of the DC bias point. And when doing so, we are actually interested more in the large signal S parameters. And to do this, we need to run both a PSS analysis and a PSP analysis. The PSS analysis is set up as such. We're going to output a lot of additional harmonics because large signal simulations are very nonlinear and will generate additional harmonic content. And we're also going to choose a conservative accuracy default and allow some additional time for stabilization because we have large memory components that will take some amount of time for the initial transients to settle out. Because we're interested in the S parameter information around a large signal bias point, we run the PSS simulation in conjunction with a PSP simulation. The PSP simulation, we set it very similar to the S parameter simulation. We select a start and stop frequency, tell the simulator which port we're going to be looking at, give it a port number, and also which harmonic we're looking at. Since we want to find the operation around 5 gigahertz, the setup looks something like this. Select OK and enable these two analyses and run. In this case, we see that the capacitance is actually quite different with a large signal perturbation than it was with a small perturbation. The small perturbation showed a capacitance of approximately 900 femtofarads, whereas the large perturbation shows a capacitance of approximately 2 picofarads. Don't be concerned with this large spike in the middle. This is due to the perturbation source disrupting the admittance around this frequency, but you can see that the average value is somewhere around 2 picofarads. The formula we use to find that capacitance is very similar to the formula that we used to find the capacitance for the large signal, or for the small signal S parameter simulation. The only difference is that we changed the SP analysis in this formula to PSP analysis. Everything else remains the same. And as I said before, if we wanted to, we could, instead of placing the port at the drain of the transistor, we could place it at the gate of the transistor and do the analysis for the capacitance looking into the transistor. And further, we can actually do 2-port S parameter simulations as well, or multi-port S parameter simulations. But since we're just interested in finding an impedance, we only need to use 1 port for this particular case.